Hello students, in this video we will discuss the Zeeman effect. When an atom is placed in the uniform magnetic field, then the energy level of the atom are shifted or split due to the interactions of the external magnetic field with the atoms, and this splitting the energy level of atom is called Zeeman effect. Okay, now the interactive Hamiltonian of the Zeeman effect is equal to minus mu L plus mu S dot the external field. Okay, where the mu L is equal to minus E divided by 2m into L. This is the dipole moment associated with the orbital motions. Okay, and the mu S is minus E divided by m into S, and this is the dipole moment associated with the spin, the electron spin. Okay, now we put this value into this equation, then the interactive Hamiltonian of the Zeeman effect is equal to minus n2 minus E divided by 2ml minus E divided by m and S dot external field. Okay, then we take common this and minus is applied to this, then E divided by 2m, and then this is L only, and first here 2 multiply here and here, then the 2s dot external field. Okay, now E divided by 2m and L plus S. Okay, this can be written this, and then the external field. We know the total angular momentum J is equal to L plus S, the orbital angular momentum and the spin angular momentum. Then E divided by 2m is J plus S, and then the external field. Okay, this is the interactive Hamiltonian of the Zeeman effect with the atoms. Okay, now the Zeeman effect depending upon the relative strength of the external and internal fields. Okay, now there is three cases are possible. The first one, when the external field is very small, the internal field. Okay, this is the weak field. The weak field of the Zeeman effect. Okay, this is the weak field. In this case, the pi structure is dominant, and the interactive Hamiltonian of the Zeeman effect can be treated as perturbations, because they are very small, and very small due to the small change in atom. The small change is we call perturbations. Okay, the next case is when the external field is greater than the internal field, and this is the strong field. Okay, and Zeeman's effect. Okay, in this case the Zeeman effect is dominant, and the pi structure can be treated as a perturbations. Okay, The next case is the when the external field is approximately equal to the internal field. In this case we use the degenerate perturbations theory. Okay, and this case is the intermediate case. Intermediate case. Okay, field of the Zeman effect. Okay, now we will discuss these all cases in the detail. The first case is the weak field the weak field Zeman effect. Okay, when the external magnetic field is less than the internal field, this is a weak field of the Zeman effect. Okay, in this case the pi structure is dominant and the Zeman effect is can be treated as a perturbations. Okay, and the good quantum states are N, L and J and Mj. Okay, these are good quantum states too. Then we apply the first order perturbations theory. The first order perturbation theory, the first order energy correction due to the Zeman effect is E1Z is the N, L, J, Mj, these states, the good quantum state, and then the Hamiltonian of the Zeman. Okay, and Mj. This is the first order energy corrections to the Zeman effect. Now we put the Hamiltonian this ones. Okay, we can put this value and this, and then this is equal to E divided by 2m, and then J plus S dot external magnetic field. Okay, this is the first order energy corrections, and this is the equation first. Then first we find J plus S, and then fourth, then they will get the first order energy corrections. Okay, now we know the J is equal to L plus S, and this is the total angular momentum is in constants. Okay, now we can draw a figure. This is a J vector. So these are fixed. Okay, and this is L and this is S vector. Okay, the L and S are precise around the fixed vector J. This J vector is fixed, and these two vectors are precise around the J vector. Okay, like this. Then we draw a projection of the S on the J. This is a projection. Okay, now the average value of S is equal to the projection of the S on J divided by J, and J here, then the square. And the mathematics we can draw or we can write the A projection on V. Okay, and then we can write A dot V and divide by V. Okay, when we multiply V here, this also V and this is square like this. Okay, then first we will find the S dot J. Okay, then we know the J is equal to L plus S. Then we can write here the L is equal to J minus S. Now we squaring both sides, then is L square and J minus S ka whole square. Okay, and then the L square is equal to J square plus S square minus 2 J dot S. Then we will find the J dot S. The J dot S is equal to, we can transfer this and to this side, and the L is transferred to this side. This is equal to J square plus S square minus L square and to divide by 2 here. Okay, this is 1/2 this value. This is the value of J. Now the eigenvalue of the J dot S is the expectation value of this is equal to 1/2, and we know the J is equal to J into J plus 1 into h cut under root in this. The J square is equal to J into J plus 1 and h cut square. Okay, and similarly for S and L. Okay, then we can write this, we can take common the h cut square. Okay, and this is J into J plus 1 and plus S into S plus 1 minus L into L plus 1. Okay, then we know the L plus 2S expectations value is equal to J plus S. This is so simple. Okay, now we put the average value of S here, and this is equal to the S dot J divided by J square into J. Okay, now we take common J, then this is become a 1 plus S dot J and J square into J. Okay, now we put the value of the S dot J, we will find here this value. Okay, then this is equal to the L plus 2S expectation is equal to the expectation of 1 is 1. Okay, and then plus this value, the expectation of this is equal to h cut square divided by 2 and J plus 1 plus S into S plus 1 minus L and L plus 1. Okay, and then the expectations of J we can write here. Okay, divide by this J square. The J square is J into J plus 1 h cut square. The h cut square is cancelled to h cut square. Okay, then we can write this is again, this is 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1. Okay, and divide by this value, and the 2 is also here, 2j into j plus 1. Okay, and then the expectations of j, this is equal to the L plus 2s expectations. Okay, now we put here for spin half particle, then we can write here for s is equal to half, then this is equal to 3 divided by 4. Okay, now we can write again, and this is equal to 1 plus j into j plus 1, and plus first we write L. Okay, minus L into L plus 1, and then the value of the s into s plus 1 is 3 divided by 4, and simple the expectation of j, divide by this value, 2j into j plus 1. Okay, and here this value in the bracket is known as the lengthy g factor. Okay, and then we can write this into the other side is the L plus 2s is equal to, we can represent the bracket term in the lengthy g factor is j g j. Okay, and then the expectations of j. Okay, this is the expectation of j. The expectations of j is equal to mj h cut. Okay, now this is equal to m g j is mj h cut. Okay, now this is the value of the L plus 2s. Okay, this value we will put into the equations this equations. Okay, here we put the value of the j plus s expectation value in the first order energy corrections. Okay, then we can write we can write E1z is equal to E divided by 2m into this value gj mj h cut, and then the external magnetic field. Okay, then here E divided by 2m h cut is equal to mu of B, which is the Bohr magnetons, and its value is equal to 5.7 10⁻⁻⁵ electron volt divided by T. Okay, Tesla, this is Tesla. Okay, then we can write this equations is E1z is mu B and gj mj and the external field. Okay, Now the total energy include both the spin orbit and the Zeeman effect. Now then we consider the ground. For the ground state, let's say for the ground states, state we know n is equal to 1, then the value of L is equal to 0. Okay, then we know the J is equal to L plus half. Then the value of the L is equal to 0 put here, so then J is become half. Okay, this is the value of this. Okay, now we find the energy for the ground states. Okay, the energy is equal to this energy we already find for the ground state, but we find again is minus 13.6 divided by n square electrons volts and 1 plus alpha square divided by n square into n divided by j plus half and minus 3 divided by 4. Okay, we put here the value of n and j, then we will get for this state is 1 and j is half. Okay, is equal to minus 13.6 electrons volt and 1 plus alpha square divided by 4. We can simplify this. Okay, then we will get test. When we put the value of n and j in this equation, then we will get test. Okay, this is the ground state energy in term of the fine structure constants though. Okay, then we the total energy is consist of the Bohr energy, the spin orbit coupling energy and Zeeman effect. Then the total energy is equal to minus 13.6 electrons volt, 1 plus alpha square divided by 4 and plus minus mu b. Here we put the value of the Zeeman effect as mu b and ji and the external magnetic field and mj. Okay, now we will put the value of the ji and the mj from this value of the n, from this value. Then first of all we will find the value of the ji. Okay, then the gj is equal to this value is equal to 1 plus jj plus half, jj plus 1 and minus L into L plus 1 and then 3 divided by 4. Okay, and divide by a 2j into j plus 1. Okay, now we will put the value of j and L. The L is 0 and the j is half. Then 1 plus this is 1 half plus 1 and plus 3 divided by 4 divide by a 2 and 1 half and 1 half plus 1. Okay, now we can simplify this. Then we will get 1 plus this is 3 divided by 2 and multiply this 3 divided by 4 and plus 3 divided by 4 divide by this one, this is cancelled to this is 3 divided by 2. Okay, then again simplify this, then 1 plus and this is equal to 6 divided by 4 and divided by 3 divided by 2. The 3 is cancelled to 6, 2 and there is 2, the 2 is cancelled to 2. Then 1 plus 1 is equal to 2. the value of the G J is equal to 2. Okay, we find this, and the value of the Mj is plus minus 2. Okay, they have 2 value. And then we put here this value into this equations. Okay, then it is equal to minus 13.6 electrons volt alpha square, not this is 1. Okay, 1 plus alpha square divided by 4, and then this is plus minus. Okay, the value of the Mj is plus minus and half, and then the value of the Gj is 2, and then the external magnetic field and the Bohr magnetons. Okay, then this 2 is cancelled to this. This is equal to minus 13.6 electron volt, and then 1 plus alpha square divided by 4 plus minus the external field and then the Bohr magnetons. Okay, now we draw a figure between the energy and the external field. This is energy and this is the field, the external field. Okay, and also with the Bohr magnetons. Then here this is the energy, and this energy here, this energy is equal to minus 13.6 and 1 plus alpha square divided by 4 electrons or this energy. Okay, when the external magnetic field is not applied here, then this is the energy. When the external magnetic field is applied, then this energy is split into the 2 states. Okay, the one is Mj is half plus half, and the other one is minus half. Okay, the slope of this is positive one and the slope of this is negative ones. Okay, and this is thank you.